little immunology. So I'm going to flip this into PowerPoint presentation mode, and when I do that, it's actually going to write the words that I say kind of as I say them on the bottom of the screen. So I'm going to be closed captioned. And when these go up on YouTube, there's always going to be a little CC button down at the bottom. If you want to see at least YouTube's best attempt at the words I'm saying, then click that. It'll get some of the science words a little bit wrong. I don't have time right now to go back in and edit all of those, but it may help a little bit. If there's something that I say that's an unfamiliar word, for example. So, all right, let's try this and kick it off. Okay, so what you've got here are different classes of immune cell proteins. Yeah, which is not the first slide. That is a later slide. So here we go. All right. So the immune system is actually built of several levels. That's the way that it's taught in some books. And I'm stealing this from a microbiology textbook, and I like the way that they introed the immune system there. So the first level of your immune system is basically not coming into contact. It's basically barrier measures. And so these would be like your skin and tears are going to contain an enzyme called lysozyme. And they're going to be parts of your body that have a very low pH. Yeah, you'll have all digestive enzymes running up and down your gut. And these things are going to be natural barriers. They're going to destroy a lot of bacteria and a lot of viruses so that very little actually gets through. And the rest of your immune system is just going to have to clean up what's left. So beyond that first level, you've got two other big levels. One of them is going to be what we call the innate immune system. And so here it is, innate, right here. It's an old word that means from birth. It comes from Latin. And so innate cells are cells of the innate immune system are things that you do have from the time you're even a tiny baby. And so what these cells do, there's lots of different types, and we're going to cover those in another slide or two. But they will do a couple of these activities over here. So phagocytosis means they'll just grab things and eat them. They'll eat bacteria, they'll eat viruses, and just chomp them up that way and destroy them. Really neat. Inflammation is just kind of a generic response. So inflammation is what's happening in your nose and lungs when you get an allergy. It's what happens in your finger when you prick it and it swells up. It's what happens in SARS coronavirus 2 inside your lungs when you get a really bad infection. You get inflammation down in there. And depending on where the inflammation is and how severe it is, that can be very bad for a person. And then you got your third level down here, which is called the acquired immune system. And unlike the other two levels, the third level, which are T cells and B cells and all their friends and relatives, these cells they have a memory. They have a way to be able to remember previous infections so that you can make a faster response if you run into the same thing again. Now, it doesn't always work like with the flu virus. Generally, your immunity won't last more than a year or two. But during that time, if you are reinfected, like if you've got rid of it, somebody else in your family has it and would be giving it back to you, your body will just deal with it and you won't have to worry about it. So it's nice. Okay, quick look at some of these physical defenses. Down in your throat and lungs, you actually have a lot of these little ciliated cells, and so these are the cilia on the outside, and they are going to beat, and they're going to move the mucus up and down. We now know that the new coronavirus can infect some cells in this area. We're not sure, but coronaviruses do often get into ciliated epithelial cells, so cells on the surface, like the skin inside of your throat, that have cilia on them. So it would make sense in some ways. It'd be very standard. And then, that's just one. All right, when we're talking second level, we're going to have to get into some of these different cells. These are just little pictures showing you what we talked about. They're going to be cells that will just react to a generalized sort of danger. They'll just go to the site of the danger and either release some chemicals or release some proteins, or there's some of those cells that will even just blow themselves up at the site and try to strangle and trap as many bacteria or viruses as they can. And they all have a role to play, but you generally don't want too much of this innate immune system. Too much innate immune response and not enough adaptive, the sort of smart immune response, usually will result in very severe disease or, in some cases, in death. All right, so here are some of the cells. Have a look at these. So all of these cells that we're going to talk about come from one population of stem cells that you would find living in the bone marrow. They're called hematopoietic stem cells. And so when you've got somebody and they have a disease like leukemia is a white blood cell related disease. So what they'll do is they will wipe out all of the white blood cells in this person, and they'll do a bone marrow transplant. And most of the bone marrow, doesn't really matter, but there'll be a couple of these stem cells, these hematopoietic stem cells in there. And so you need them to divide a little bit and make more hematopoietic stem cells, and then you need them to differentiate into everything else. And theoretically, if you get one of these guys in there and it starts functioning, you can build an entire immune system from it, which is pretty darn cool, isn't it? And the other neat thing is that they build everything from red blood cells and platelets through the innate immune system up to the adaptive immune system. And they all come from the same stem cell. Ugh, there we go. All right. Anyway, so at the first level, we got two different ways we can go. We can turn into a myeloid stem cell, which means we're going to be one of the dumb guys, or we can turn into a lymphoid stem cell, which means we're going to be some version of a white blood cell. And there are a couple versions down here, like T cells and B cells. Those are some of the famous ones. But let's go over here and let's look at the dumb guys first. All right, so our myeloid cell is going to differentiate again. It'll keep dividing, and some of its children can go on to any of these different fates. And what happens when with a particular cell is going to depend on which signals it's getting. Like what are we running out of? What do we need more of? And then it'll differentiate and fill those. So red blood cells over here actually come from a thing called an erythroblast. Now, an erythroblast has a nucleus, but red blood cells do not have a nucleus. So red blood cells are, you could almost call them not technically alive. They're like a cell that doesn't have a nucleus and can't do a whole lot. They're good little carriers, but they're not really set up to respond well to the world. There are some animals, though, like rabbits, that still have a nucleus in their red blood cells, and so they look a little bit different. But that's red blood cells, and that's why they look the way they do. They look like somebody scooped the nucleus out, right in the middle there. Okay. And you've also got these guys. So megakaryoblast give rise to megakaryocytes. These are giant cells, and all the time they are chopping off little bits near the edge. And these little tiny bits of megakaryocyte, there we go, are what we call platelets. Platelets are the things that are going to be involved in blood clotting, and they are definitely involved in inflammation. Inflammation is like that sort of redness, pain, heat, loss of function. And there's one other thing, I don't know, it's coming up in a later slide. This is the inflammatory response. This is our generalized reaction to any sort of danger or damage. This is just what the immune system does to try and protect you. But yeah, so that's a platelet. So also not a cell, just a little tiny piece of a cell, not really truly alive. And it's kind of weird to think of your red blood cells and platelets, which are both really common in your blood, as being not quite alive. Yeah, given that they're what keeps us alive. But hey, that's science. Okay, so down here we've got our myeloblast lineage, and that's fine. It's going to give rise to these things that we call granulocytes. And you could call all four of these goofballs, mast cells, neutrophils, basophils, and eosinophils. They are all granulocytes. They're called granulocytes because inside they have all these little pockets, these little pouches. You see them? And these are filled up with proteins and chemicals that can be released to fight infection in general. And if you were to take an immunology class like the one that I'm going to offer next year, we would go into some of these chemicals and what they do and how they work. And there's going to be some of those chemicals that are going to be important for the cytokine storm coming up later. That's where we're going to in our final level today. Anyway, what's the difference between these things? Okay, so mast cells are going to live in tissues. And they are going to be a cell that is going to trigger local inflammation in a tissue. So you stub your toe swells up, it's going to be mast cells that are driving this thing. They're also super involved in allergy. They have a way to pick up the kind, well, actually, no, mechanism doesn't matter for this class, but they have a way to pick up another component of the immune system called an antibody. And there's one special type of antibodies that tend to be involved in allergy. And they just set off mast cells. It's like the 4th of July. And given that this is allergy season, I think that's quite relevant. Okay, so mast cells live in the tissue. If you have that same sort of cell, but it's in the bloodstream, it's going to be a basophil. And so a basophil is just your basic granulocyte. That's how I remember it. Mast, I think like if you had a mastectomy, they would be operating on one breast. And so that breast tissue would have mast cells in it. If that helps you, fine. If not, whatever. Come up with your own way to remember it. That's fine by me. So your basic basophils, your mast cells, fine. We got those. We got two other ones here. One of those is eosinophils, so it's these guys. And they're called that because there's a dye called eosin that's this sort of hot pink color. And eosin happens to stain them very, very well, and it doesn't really stain the other cells of the immune system. So they just show up as nice fluorescent pink if you put the right stain on there. These are cells that used to be involved in fighting parasites for the most part. So like worms and fungus. And now that we live a lifestyle that means that we don't come into contact with quite as many worms and body invading fungi as we might have in caveman times. These things are basically cells that don't have a whole lot to do a lot of the time. And so these are also going to be involved in allergy. And so if you take one of those little things that you squirt up your nose at night to try and sort of clear your sinuses so you can get to sleep, which I definitely do during allergy season, they're going to contain a steroid, and the point of the steroid is that it will actually kill off some of these eosinophils. Now, they grow back. They'll grow back within a couple of hours. That's why it says, one spray will last you a day or something, but it doesn't last any longer than that. But there you go. That's what you're doing. That's why. The other one of those granulocytes are called neutrophils. Now, these are the most abundant of all of the immune cells, if you like, in your bloodstream. There are tons of these, and they are absolute maniacs. So they will go in, and they are phagocytes. They will eat other things like bacteria and viruses. They're also, they've got a lot of little granules that they can release, and so they'll call in other kinds of attack. And the neatest thing they do is that they will actually explode themselves near a site of danger, and their DNA has these special sticky proteins all over it, and it forms something like a net that basically traps bacteria at the site. So neutrophils are like your own personal little bodyguard that loves you so much that it'll strangle anybody that tries to get you with its own intestines. Yeah, that's I think that's the good metaphor there. But they'll use their very own DNA, and they'll explode in the process of doing it in order to keep you going. Yeah, because they love you, man. Okay. So over here, the last bit of the sort of ding-dong side of the immune system, these innate guys, you're going to have monoblasts, which just go on to make monocytes. Now, monocytes are going to float around the blood. These are the non-activated version, and they're just kind of big but round. They could theoretically activate, and when they activate, they turn into one of two things. They'll turn into macrophages, or they'll turn into dendritic cells. Now, these guys have very different roles in the immune system. So the monocytes here turn into macrophages, and macrophage literally means big is macro, and phage is eat in Greek. And so they are big cells that eat things. They are big eaters. And these big boys will, and so you see, these are like hydrodynamic. They're ready to flow around in your bloodstream and not bump into anything. When they get activated, they get all spiky and just like a splat. They try and stick to the wall, and they will burrow through your veins and try to go into your tissue and find the site of damage. And they have all kinds of stuff that they will use to try to kill whatever is making you sick. Now, macrophages are pretty forceful. They can produce a very strong immune response, and normally that helps. What they're doing is buying time for the smart side of the immune system, which is these guys over here, to kick in, because these guys need about a week to get everything together to fight an illness. But macrophages are your first line of defense. They're there to slow down the virus or the bacteria. But macrophages are also responsible for most of the damage that you get in lungs with a disease like the new coronavirus, for example, or bird flu, or even Ebola, is mostly caused by macrophages when they're doing too much for too long. And so you want a little macrophage activity, but you don't want too much. Yeah. So macrophages are monocytes that are running around the bloodstream, then get activated and then burrow into the tissues to attack. Dendritic cells are monocytes that went out into, think like your fingertips and toes. It's really, we call it the periphery. Just anywhere that's kind of away from the main veins and arteries in the body. Any one of those tissues. And they will embed themselves in the tissue and they will just hang out. So a dendrite is kind of a long, thin finger of cell. And so dendritic cells do look like this. They're all sort of stretched out, long and thin. And yeah, some of these will move around in the tissues. Some of them will just embed themselves in the tissues and they will grow old with your muscle or whatever it is, a little chunk of skin. But whenever there is damage at that site or whenever you get an infection at that site, then macrophages are the biggest little tattletales in your immune system. They're going to pick up a little bit of whatever it is that's caused the damage, and they're going to bring it to show other cells of the immune system. And so macrophages are going to go tell the teacher. And in this case, the teacher is going to be a T cell or a B cell. And dendritic cells can go and interact with both of those. Okay, so we've covered the dumb guys, dumb and brutal and effective, but kind of damaging. So that's your innate system right up to there. And then over here, this is going to be your adaptive immune system. And so you got your lymphoid stem cell, which is going to give rise to several different things, NKs and T cells and B cells and a bunch of other cells. There's a bunch of other flavors of these things. Like I'm going to mention I'll mention 4 kinds of T cells, but there are actually many more that you'd run into as an immunologist if you're somebody that studies this. But for now, we don't need all of those to get the general concept, because that's what we're going for here at level 1. Your B and T lymphocytes do 2 important things. So T cells have 2 jobs. There's 2 main kinds. These are the helper T cells over here, and they are going to help other T cells, and they're going to help cells that produce antibodies called B cells. And then you've got your killer T cells. Now, your killer T cells are going to actually go out and destroy any cell in your body that is making the wrong kind of protein, that's making a protein from a virus or bacteria. And so killer T cells are the thing that actually protects you. And in diseases where people die, generally they're going to make this innate immune response because, that happens all by itself. But generally the difference between living and dying from something like Ebola or coronavirus is going to be whether or not and how quickly do you get to activate these killer T cells. And the faster you can activate them, the faster you will actually get better. It seems paradoxical, right? They come in and kill other cells in your body, and yet that is their job, and it really helps. They do a great job. So thanks, killer T cells. Killer T cells have a protein on the outside called CD8. And that is the thing that sort of marks them. That's how you can tell a killer T cell. Helper T cells are the other ones. And so they have a marker called CD4. And that might sound familiar, right? Do you remember back to HIV? Yeah, I bet you do. HIV uses CD4. So HIV is going after specifically your helper T cells. And helper T cells are like, I like to think of them as little 4-star generals. So I imagine that's what the 4 stands for. It doesn't. It stands for CD4, and yeah, it's just the fourth protein that somebody named of this type. But yeah, if you imagine them as 4-star generals, and you imagine killer T cells as these just loony tunes that wear, like, you ever seen somebody that wears one of those 8 balls, on a hat? Anybody that's wearing that, they've got at least one screw loose. And so I think of those as the killer T cells. Yeah, generally not bad people. Just, yeah, don't get too close. All right. So boom, helpers, killers, great. Those are some of your T cells, but we've also got these other guys. So they're regulatory T cells. These are going to be called T-reg cells by most immunologists. And they signal when an infection is over, and they turn off the other T cells. Because once you have defeated the danger, the infection, you want to stop that inflammatory response, because in general, that's not a good way to live. Yeah. Inflammatory response is bad for you in the long term, but in the short term, it helps enough for you to defeat bacteria that it's worth it. Well worth it. And then the last one you've got are memory T cells. These are cells that are essentially veterans. And so these are cells that used to be a killer T cell or a helper T cell. You remember back in '09 when you had that cold? Yeah, your memory T cells, remember. And these things are preserving. So the way T cells and B cells work is they actually change their DNA. And when they finally have changed it enough that they can match whatever the new disease is, then this is great, and that's when your response really gets going. A memory T cell preserves a couple of those cells in their final state, ready to go back and attack whatever that thing was that you had before. And so this is how we can make a faster immune response next time. So you might get sick from a virus the first time you get it in a year, and then the second, third, fourth time that it comes along, your memory T cells will just wake right back up and whack that thing before you even know that you were infected, which is very nice. So B cells will differentiate into a thing called a plasma cell, and those produce antibodies, which are a Y-shaped molecule that kind of acts like a handle. The antibodies will stick to viruses and bacteria. And there are a couple of things that they do. They can lead to other proteins that clip on there and will directly destroy the bacteria, or they can act like a little handle and help something like a macrophage pick up lots of bacteria and just gobble them up, which is really cool. So yeah, that's what B cells are for, and plasma cells. Helper T cells support these B cells and help them to differentiate and make sure that they do the right thing and make a response. And then the last one in this group are the natural killer cells. So these are like, I don't know, old East German secret police maybe. What they're looking for is cells are supposed to be showing a little piece of whatever protein they're making all the time. That's the cell's job. And there are a lot of infections that will cause the cell to not show what it's making. Because if a cell shows that it's making a little bit of virus protein, then you're going to get killer T cells coming in and smacking that cell around. Yeah, it's going to die. But so it causes a lot of cells to just stop showing whatever they're doing. Go secretive, if you like. Go dark. Natural killer cells look for this among their many other functions. And if they notice a cell that is not showing what it's doing, they just stop and they kill it, whether it's infected or just a little defective at the moment, or maybe just, having a lazy off day. It's okay. You don't want those cells around, and your natural killer cells are just going to take care of that for you. So that's why they're called natural killer cells. They can kill other cells even when there's not an infection, because they're not looking for infection. They're looking for something that correlates with infection, cells that aren't showing what they're doing. So I think that's a good point to put a break in this talk. That's probably enough for one go. And we'll be back with some other parts of this immunology lesson. Thank you.